Today's code for the class is 1989. I'm going to say it again. Today's code for the class is 1989. This video is going to sound very familiar because a dehydration reaction is basically what I talked about last day of class when I was talking about elimination reactions under acidic conditions. A dehydration reaction is just like a dehydrohalogenation, in which is a beta elimination. But in this case, in a dehydrohalogenation, what's leaving is an H and a Cl or a Br, some halogen, and that is in position alpha. In this case, what it's going to leave, it's a whole molecule of water. So sometimes you'll see dehydrations to show that a molecule of water is being lost because we take that hydrogen that is at the beta position, and the leaving group is going to be the OH. But at this point, what you know is that that OH is not going to be a good leaving group. So in order for that OH to leave, something has to happen. So what needs to happen for that OH to leave is that it needs to become a good leaving group. So it's usually carried on under acidic conditions, very strong acid, because you need a very strong acid to protonate that oxygen right there, right? So as we talked about in that video, sulfuric acid, when mixed with water, that will give us hydronium ion, and so the OH will go grab one of those hydrogens, and then it will become water, making it a good leaving group. And then the base could come, grab one of those hydrogens, and give us that pi bond, that new pi bond. And paratoluene sulfonic acid is a very, very strong acid. I would like you to think, why do you think that paratoluene sulfonic acid is such a good acid? Think about how would the conjugate base of this paratoluene sulfonic acid would look if that hydrogen is gone. So this is how that SO3, right? So we have the ring, right? So this will be the conjugate base of paratoluene sulfonic acid. It's very stable, and that's why this compound is very, very acidic. So the more substituted my alcohol is going to be more reactive, because remember that alcohol is going to get protonated, right? And so then that, because this is going to give rise to a more stable alkene. That's why there's as we go up, so as we go from a primary, secondary, tertiary alcohol, this one will give us a more stable product, right? It will give us a more substituted alkene. So that's why tertiary alcohols are the most reactive in this kind of, in eliminations in general, right? And this has to do with the Zaitsev rule. The major product, remember that is going to be the more substituted alkene, and the minor product is going to be the least substituted alkene. So there have to be different beta carbons, and the ratio selectivity will tell us that the major product is the more substituted one. This is called the Zaitsev rule. And remember that the minor product, we usually call it the Hofmann product, right? So I already talked about it in previous videos, so I'm not going to repeat that again. And so the mechanism, what will happen is you will get that OH protonated. So sometimes you will see it as the sulfuric acid, or sometimes you will see the hydronium, right? In both cases, it's correct. So that will get protonated, that will give us water, and that for the formation of the carbocation is the slow step. But then once the carbocation forms, the conjugate base of that acid can act as a base, can grab that hydrogen, and that will give us the double bond. So the E1 dehydration will give a mixture. What usually happens is that we will get a mixture of SN1 and E1, and the reason for that is because we go through carbocations, and so that will give us a mixture of the two products. But in the E1 dehydration, when we use an acidic condition, that doesn't happen, and so we will only get clean dehydration. So that will mean that we will get E1. So we usually get a mixture of SN1 and E1 when we go through a regular base, a regular SN1. But in the case of E1 dehydration in the presence of an acid, that doesn't happen. And for an E2 reaction to occur, the exact same thing. So we get the alcohol that gets protonated, and then the conjugate base of that acid that we started with can come, and that will give us the double bond, and now we have a good leaving group. Now, here we have a contradiction, kind of, because the entropy of this reaction will favor the product formation, right? Because we have, in the dehydration, we start with 1, and then we end up with 2, right? So the entropy will increase because we go into two molecules, and we start with 1. But the enthalpy will favor the reactants because we have 2 sigma bonds that are broken, and the reactant is stronger, and then we have a sigma bond that is formed and a pi bond that is formed in the products, right? So the entropy tells us that the reaction is going to go in this direction because we go from 1 molecule to 2, but the enthalpy will favor the reactants. And if you remember this formula right here, delta S, right? This value is usually small, and it can be negligible. So in this case, the entropy, even though the entropy is telling us that the reaction will go towards the products, the major contributor to this molecule is going to be the enthalpy. And so the reaction is going backwards. In order for this reaction to happen, in order for a dehydration to happen, what needs to happen is that we need to put energy, because this is an endothermic reaction. You see, if you go through the calculations, this ends up being an endothermic reaction. So the only way that we have to increase this term right here and make the reaction be that the delta G is negative, so the reaction moves towards the products, is increasing the temperature. So if we increase the temperature, then the reaction is going to move towards the right. Also, if you remember Le Chatelier, as we are progressing the reaction and more of my product is being formed, then it will, the reaction will move forward. Also, if we are removing the side product, that in this reaction is water, right? By increasing the temperature, what you do is that you get water, and then you are eliminating it. So as you are eliminating, you are using Le Chatelier principle, we are moving the reaction forward, because as the water gets eliminated, more of that starting material will transform into the products.